So hello everybody, welcome to my second session during the spring school. Today I'm going to talk about how to get rid of artifacts on mainly EEG data, but this also applies to ECoG data with a method called OSCAR you might have heard of already. So unfortunately, Sebastian and Martin cannot join today, so I'm going to do this alone. So that's you can see why. That's why I have mounted the Nautilus cap, but it seems like the Bluetooth headset is working also very well. So two Bluetooth devices on my head, that's good. So let me start with introducing a little bit the types of EEG and ECoG artifacts we are dealing a lot with. In its principle, an artifact is something you don't want to have. So this comes from a kind of an external or from a different source of the signal you want to actually measure. And you can basically characterize this in 2 dimensions. So there is a way of having physiological artifacts or electrical artifacts, and they can be either transient, so they occur only every once in a while in bursts or something like this, or they are quite permanent. So the most prominent artifact we are usually dealing with is EMG. It stems from muscle movement, and it occurs when you're actually moving your body while you're performing EEG measurements. This is a very common source of artifacts for EEG. Luckily, this doesn't happen in ECoG, because in ECoG or in invasive recordings, you have you're under the skin, so you don't capture any muscle activity. Then there is eye movement, EOG, or ocular artifacts. This happens when you are blinking, like this, or if you're moving your eyes like this. It can also happen, especially you cannot avoid blinking. This always happens, and you always have, especially in the frontal channels, you have blink artifacts all over the place. But luckily, they occur not permanently unless you're provoking that, but they're occurring every once in a while. That's why they are considered transient artifacts. Typical permanent artifact stems from the heart. So cardiac artifacts or ECG artifacts are captured when you are recording EEG close to a blood vessel. So usually when you are placing the electrodes correctly and they have good recording impedance, then you're not capturing that. But unless your heart stops beating, this is also a permanent artifact, which occurs roughly once a second. And then when you're not doing the measurement properly, or when you're doing the measurement in an environment where you are required to move, for example, when you're on cycling or you are doing exercises, then it's sometimes unavoidable, or in these cases, it's unavoidable to have cable movement artifacts. So these are very large amplitude artifacts usually. And of course, not physiological of a physiological source, but electrical source. So what also happens if when you charge up something and you get discharges, of course, this is also captured when you're recording biosignals in those channels. Sometimes EEG is measured at the same time when you're doing stimulation. So this can be, for example, TMS, transcranial magnetic stimulation, where you are recording EEG and you are injecting a magnetic pulse actually into the head with a very big coil. Yesterday we have seen an experiment. So this introduces very huge transient artifacts on the EEG. For invasive recordings, there is electrical cortical stimulation, where you are injecting current into the brain. And of course, this charge transmission also causes large artifacts on the recording channels. A very common artifact, which is also permanent, is line noise. So this usually happens at 50 Hertz and it's harmonics, or 60 Hertz if you're in the US, and it's permanent. So usually we are getting rid of that with notch filters. So what can also happen, and it's really a question whether it's an artifact or not, is pathological activity. It's very difficult to distinguish this or to to classify this because pathological activity, for example, epileptiform spikes basically spiking activity from epilepsy patients can have very large amplitudes. So this really leaves the range of a typical EEG recording and would be, for example, classified as an artifact if you're going for amplitude deviations or something like this. And it also has a different spectral characteristic than EEG. So if you're going to do some artifact removal, most likely you will end up with removing pathological activity as well. So yeah, this is basically it as an introduction. So we have thought a lot about how to deal with that. So I already mentioned that line noise can be removed with notch filters. ECG artifacts can be removed via placing electrodes correctly or well, but still there are some artifacts you cannot remove or they just happen. So we wanna figure out, or we wanted to figure out how to deal with that and how to get rid of that. So we kind of set our bar quite high and defined a few goals, what we want to achieve. So if we can imagine a perfect EEG or ECoG artifact removal approach or tool, then this would, of course, eliminate all artifacts, or at least a very wide range, such that the result is something we don't have to process further in this respect. So we can just use it, and it doesn't have any outliers, but it just contains good EEG and has gotten rid of all the artifacts. But of course, we want to preserve or even recover brain activity. So when we are doing experiments, as we all know, we can modulate our band power, maybe ERD or ERS. We have event-related potentials or evoked potentials, P300 waves and something like this. So of course, we want to preserve that. And even if it's buried under artifacts, we want to recover that. Taking that further, we also want to preserve or recover PCI performance. So this is actually one step after the brain activity or the brain features we are using for PCI. So let's say we're having a P300 speller, we want to have it very robust against artifacts. Or if we have a motoimagery system, we also want to make sure that artifacts are not deteriorating our performance. Fourth, such a system should provide us feedback whether the signal is good or bad, or if it's corrected. So there is no point in having a perfect EEG artifact removal tool, which provides us perfect signals all the time, but we don't know whether the original signal was good or it has been corrected. So we always need feedback about the underlying recording quality. Number 4, it's kind of linked to the first point. If we eliminate all artifacts, then we implicitly get realistic EEG at all times. So here I'm talking about the kind of spatiotemporal statistics, characteristics, also the stationarity, such that it's just well behaved, and we don't have to apply any outlier removal or any further correction actually afterwards. Number 6, so it gets more and more. Such a tool should work out of the box. So again, the best tool is not really usable if you have to configure and if to calibrate it extensively before you can use it. So we really wanted to come up with something that you can just start and it works. Number 7, also a very challenging point, is that although offline processing makes much sense in many scenarios, the ultimate goal would be to have something like this that operates in real time. And of course, it will have some delay, but it has a delay which is really acceptable in regards to a real-time performance of a PCI or something. So we were quite aware of that. This is a really huge wish list, but after thinking a lot about it, we came up with a concept which we call signal conditioning and artifact removal. It's very unique, and I will talk a little bit about it. But since SCAR is probably not the best acronym, we made it online. So that's how OSCAR was born. So the overall talk will be about OSCAR. The main assumptions or the premise we have when we are using OSCAR, or we had when we were designing OSCAR, were that the EEG, good EEG and artifacts, they just have different spatiotemporal properties. So they have different amplitudes, they have a different spectrum. So for example, EMG has very much, very a high proportion of high frequency components. EOG has very slow waves that are large in amplitude. So it's just, and also visually, since you see it visually in the recording, it must have different spatiotemporal properties, because spatiotemporal properties define the overall appearance of a signal. The second assumption was that those artifacts, they occur relatively infrequent compared to normal EEG. So we were not dealing with something that occurs permanently, or is just, you know, something that's in the signal, but we are focusing on something that occurs as a transient artifact, so that we have a normal EEG recording going on, and then boom, an artifact happens, and we can correct that. That's let's say the most common way of artifacts are in the signal. Because if you have permanent artifacts, anyhow, you have to change your recording strategy because the data is not usable. All right. So in very rough terms, the procedure of OSCAR is that we're going into different frequency bands. So there is a frequency band decomposition going on. When we have those individual bands, we are buffering the signals. And then we are performing a very fancy spatiotemporal whitening operation. And inside this spatiotemporal whitened space, we can now very nicely identify artifact components. We can remove them, and we can condition our signal. So we can make sure that it really complies to characteristics of EEG. Once we have done that, we are transforming back, we are inverting the whitening, we are unbuffering and serializing the signals, and we are aggregating all the frequency band signals together. That's basically OSCAR in a nutshell. The highlights of such a concept are that it's unsupervised, so we don't need any reference channel. We don't need any EOG recording, for example, or anything else that provides us any reference to the underlying artifact. It is adaptive, so we don't need any calibration. It's adapting to the data it receives, and it's automated, so we don't need any user input besides number of channels or something. But that's something that's available anyhow. But we don't have to set any, let's say, sensitivity or any parameters, any hyperparameters. That's all in the box. And working a lot with these concepts we came up with, and with reflecting on the goals we have set, we recognize that there is not really a one-fits-all solution. So we really have to identify the use cases we target, and then we were adapting the individual kind of approaches to how to apply OSCAR to the data. And we identified, or we designed basically 3 members of the OSCAR family. So let me introduce them. First one is OSCAR Live. This is what you have seen probably on Christoph's LinkedIn posts in the past. This is really the live online real-time EEG artifact removal. So this operates at a very short delay. So within 200 milliseconds, we have our output ready. We are limited to standard EEG. So we have 30 Hertz, which is enough most of the time for standard BCI control. And we can process, and that's actually new, and we're quite proud of that. We are able to process up to 64 channels in real time. The sampling rate doesn't really matter because we are anyhow band limited. So of course you can record with 2.4 kilohertz with a high amp, but anyhow the result will be band limited to standard EEG range. So the goal of OSCAR Live is to optimize the source signal reconstruction. So we are removing the artifacts, and we want to make sure that the underlying signal is revealed. Then we have OSCAR Pro. If we are not bound to an online scenario, but we really want to clean the data, we can do OSCAR, not online, but offline. Still, we have an O here, so that's correct. It's offline EEG or ECoG artifact removal. And here we don't have any limits because we don't have any real-time constraints. We have larger processing windows. We can go up in the bandwidth. So there is really no band or no channel limit. You can process all the data as you get it. And again, OSCAR Pro obviously is dedicated to optimize source signal reconstruction. So we want to reconstruct what's underlying underneath the artifacts. So these approaches, they're unsupervised. So we are just getting a stream of EEG data. We don't have any, let's say, task-related information. But when we are running a BCI experiment, we do have task-related information at hand. We know the task, maybe ID or whatever. We know more than in a free running stream. We know more than, in this case, what's going underneath. And this is when we came up with OSCAR BCI. So this is again a real-time artifact removal for EP and ERP-based BCI. So you can, for example, use it for P300 spellers. You can use it for visually evoked potentials and so on. And here we are kind of staying in this spatiotemporally whitened space and removing the artifacts and doing our classification there. And we are not transforming back to the EEG standard space. So this is why we don't get any EEG data out of the OSCAR BCI, but it's not its purpose. Here we want to optimize BCI performance, and that's what it's doing quite well. Now talking about the integration and availability of OSCAR, the OSCAR Live is currently being integrated into g.HIsys. So we have a g.HIsys demo today. It's going into g.Recorder and the Unicorn Recorder, and all g.TEC amplifiers are supported. Obviously, since Pangolin has so many channels, we're still in the planning phase. But if you're recording 64 channels with the Pangolin, that's going to be possible for sure. So here, the scenario is that it's coupled to our amplifiers, and the output signal from those amplifiers, as you record them, they are already artifact corrected. So OSCAR Pro obviously goes into an offline processing tool, and what is better suited than g.BSanalyze? So this is where you will find OSCAR Pro in the future. And OSCAR BCI is actually already integrated in a lot of g.TEC EP and ERP classifiers. So for example, the Blondie check already uses OSCAR BCI, and the Unity games, the Unity interface, which is being rolled out and I think also being demonstrated during the spring school and during the hackathon. For example, Brain Buddy and Puzzle Game. So Martin is very active here. These applications already use the OSCAR BCI. Now let's see if we can do this in real time. So I have prepared a live demo. That's why I'm wearing the EEG cap. So right now, I'm here in Simulink. I have the g.Nautilus connected. Let me see if I can access it. Yeah, looks good. So my electrodes we have 16 channels, and all those are gelled at the moment. So we have Sahara hybrid electrodes, from the Unicorn. Basically also works with dry electrodes, but it's a big demonstration, so I don't want to risk anything. So that's why we have gelled it. Here everything is happening in Simulink. We have two output scopes with clean and with raw data. And I will start the model now. I tried it with screen capture, it works. Let's see if it also works with screen sharing. So I will stay very silent in the beginning. Nice. So you can see on the left side, you can see the raw signals that are recorded right now. Looks good. On the left side. On the right side, you can see the Oscar signals. So those are the signals corrected in real time. We have 16 channels. You might have noticed that channel 6 is a bit bad. That's okay. It's floating around. Yeah, you have also seen maybe that I have already introduced some blinks to the data. They're all nicely corrected. So what else shall I do? Can shake the head. So all this is detected and corrected, and immediately afterwards, everything is going back to normal. And when the scope is white, the data is one-to-one the same. So you have exactly the original data. So it's not affecting the data when they're in absence of artifacts. Good, let's do some more crazy stuff. Maybe I will stand up. Last year during the spring school, Martin was doing a lot of physical exercises, but unfortunately I'm not as fit as he is. But I think on Friday we have a session with Martin. Friday, so Martin will probably be able to do a real-time P300 experiment with Oscar during, I don't know if I can spoiler that, during some exercise. Yeah, so you can see I'm talking casual stuff while recording EEG, and there are some artifacts in the raw data, but the cleaned data look very, very good. We still have, to be honest, some issues, but we have a fix for that already. Not demonstrated today, but we are having some issues with alpha. So let me do some alpha. Sometimes it's corrected, but we're, yeah, well, not now. Yeah, so that's nice. Visually, it looks good, I would say. What else do we have? Maybe some crazy eye stuff. Yeah, so we can simply say that the channels that are connected fairly well in general, they are corrected very well. As I said, channel 6 is a bit nasty. So sometimes the correction is not so good. It's basically because Oscar has adapted to the spatiotemporal characteristics of channel 6. So it allows it a bit more to fluctuate because it has been presenting itself as a channel with fairly large amplitudes and slow waves. Yeah, so before I lose myself here, I will stop that demo and do something that makes a bit more sense. Because I have also prepared a visually evoked potentials paradigm that I will start now. So this paradigm consists of a series of images that are shown to me randomly. All of them are grayscale, but one of them is in color. And usually this is the purpose or the principle of an oddball paradigm. When a stimulus that deviates from the other stimuli occurs in a pool of those stimuli, then, and you're focusing on this stimulus and you may be counting it, then you react, your brain waves show that as a P300 wave. And here in this case, even if I don't really concentrate on that image, we will see that as a visually evoked potential. So let's see if that works. The paradigm is loaded. Let's start. We have a few scopes again. So I will do this experiment now, and you can have a look at the EPs that are generated. It's finishing soon. Oh, no. That's a good internal clock I have. Yes. Stop the model and discuss the results a little bit. So you have seen that I've done lots of stuff you should not do during an EEG experiment. And lots of the channels are contaminated with artifacts. You really cannot use them. But still, the response, and you have to look at the scaling, it's plus minus 10 microvolts. So this is still in the range of several microvolts. I have a consistent response with Oscar. Maybe I show you a result I recorded from before the presentation, because there it is easier to see. Yeah, I'll close that now. So that's enough about real-time demo. So here in this experiment, right before the talk today, I did the very same. And what was very nice to see was that even though we are really operating in a very narrow time scale, we are producing very fast results. The response here is quite consistent. So we expected kind of an evoked potentials due to the target stimulus, the color image, and all those channels, they showed that although the original channels really had lots of artifacts on them, we still got very consistent evoked potentials in a scale of several microvolts. So that is the results and live demo of Oscar Live. So let's hop over now to Oscar Pro. Let me check how much time I have. Still a couple of minutes left. So Oscar Pro now moves the focus from real-time performance with results that are available as fast as possible to a very profound and deep removal of artifacts. This is why it's called Pro. And what we tried to assess here was really how good its ability is to reconstruct the source signal. So what is there before the artifact was contaminating the data. So since we don't know it, there is no ground truth available in contaminated data. We had to create our EEG data to get this ground truth. So that's why we used some artifact recorded data, and we extracted those artifacts from EEG and removed all the EEG with a quite sophisticated methods. So in the end, we got quite a couple of nice template artifacts, and we took artifact-free recordings. So those artifact-free recordings are our reference signal, and then we applied those artifact templates to our reference signal. So this created our contaminated signal. And then we processed this contaminated signal with Oscar Pro, and then we got the cleaned signal. So we have 3 signals we can compare. So before we go into the quantitative analysis, let me show you a few examples. This is a time course of 16 channels EEG, where green is the reference, red is contaminated, so you can clearly see that we have some, I guess it's EEG artifacts over there. And when we apply Oscar Pro, then we get the clean signals in blue. And already visually you see how well the clean signal matches the reference signal. So that's a quite nice output. And also here, we have the same structure. We have a reference signal in green, contaminated in red, and cleaned in blue, even with some alpha on it. But the artifact is removed while the alpha here, for example, is preserved. So again, we see visually a nice reconstruction of the underlying reference signal. So how did we put that into numbers? So first of all, we had a look how much we actually compared. We computed a similarity between the signals. So we had a look how the contaminated signal compares to the reference signal. Basically, it's completely different because we have an artifact there. So there's lots of information gone because the signal is contaminated. So this was our baseline. And then we compared the cleaned signal to the reference signal, which should be similar if Oscar Pro is working well. So this allowed us to determine the recovery of the signal. So how much of the source signal is recovered. What we did was we kind of correlated the signal. So we computed the squared Pearson correlation coefficient. That's the coefficient of determination, or R squared value. It ranges from 0 to 1. And if it's 0, then the 2 signals have basically nothing in common. And if the value is 1 or 100%, then the 2 signals are perfectly identical. So since we applied artifacts to the data, we knew that, or the resulting data, contaminated data, consisted of kind of good segments and bad segments. So we analyzed those separately because we wanted to make sure that the good segments are not deteriorated, and we wanted to make sure that the bad segments, those with artifacts, in those bad segments we get a nice recovery of the reference signal. We also had a look at different frequency bands. So at the broadband, the overall EEG, of course, but also we looked into the delta, theta, alpha, and beta band. And the coverage was quite extensive. So we had 5 subjects, recording from 5 subjects with 16 channels. We used data from 2 BCI experiments. Then we applied 5 types of natural physiological artifacts that just can happen if you're doing an experiment, and 5 types of provoked artifacts if you're doing something bad, like touching your head, what you shouldn't do. So we had 5 types of natural and provoked artifacts each. Then we had 3 levels of contamination. So low contamination, 25%, to huge contamination, 75%. And we repeated, like we realized this generation of data sets 5 times for each subject type and contamination level. So this is how we reached 1,500 data sets in total. So it's quite an extensive coverage. And this is the result. So here we have the comparison between contaminated signal and reference signal. You can see that the good parts of the signal, they are kind of identical. We have some outliers in the very low frequencies. Okay, fair enough. But basically the good segments were not affected by adding artifacts because the artifacts were only added to the bad segment. So that's what we wanted to have all over the overall across all frequency bands. And as expected, the artifacts really let the R² value drop a lot, especially in the delta band, the low frequency part, but also tremendously in the theta band and the beta band. Not so much in the alpha band, because in the alpha band, the artifacts were not so present. So that's all expected. Now, when we applied OSCOR Pro, this is what happened. We really improved the similarity, the R² value, for all frequency bands, and also for the overall broadband EEG substantially. So in the end, we can say that the large parts of the underlying source signals have been reconstructed, right? So taking that further, we have gotten rid of the artifacts. We're quite satisfied with the signal reconstruction, but how does this translate to BCI performance? So that's also something we investigated. So luckily, those data sets already contain some BCI paradigm, so we used that, and we computed the BCI performance on those data sets. We used 20 training trials, randomized, of course, and to get the actual performance, we used 2, 4, and 6 test trial averages, all randomized, of course, not from the same trial pool, and we repeated this 200 times to get stable results. And here we now compared the BCI performance loss in the first place. So the initial performance loss, which happened when we contaminated the signals. So it's basically contaminated minus reference. And then we had a look at the remaining performance loss. So the performance loss we still have when we apply OSCOR Pro. So that's basically the performance of cleaned minus reference. And when we look at this graphically, we can plot all that nicely in a 2D scheme, where on the x-axis we have the initial performance loss. So the more it goes to the left, the worse it gets due to the artifacts. And on the y-axis, we have the remaining performance loss. So the more it goes down, the worse it is, even though we have applied OSCOR Pro. So those exemplary plot dots here would then be data sets, and we got lots of them. But let me talk a little bit more about how to interpret this graph a little bit more. So we would all agree that when we have all the dots on the 45 degrees line, we would say that the BCI performance has not changed, because we have initially and after applying OSCOR the same performance loss. There is a lower triangle. So if we're going into this direction, then Oscar Pro has even deteriorated the performance, something we don't want to have. And the upper triangle would show that the BCI performance has been restored, at least partly. And if we are up here on the green line, Oscar Pro would have completely restored the BCI performance. So let us have a look how the results are. This is when we apply Oscar Pro to all our data sets we have generated. Initially, we have a performance loss of about 19% due to the artifacts. And after applying Oscar Pro, we only have a remaining performance loss of 3%. So we're going down from 19 to 3% performance loss. So that means Oscar Pro can recover 84% of the BCI performance. That's a very nice result. Now, Oscar Pro, as you know, now is an offline tool. We can nicely restore BCI performance, but that doesn't help because the BCI experiment is already over when we are processing the data. So let me talk in the last couple of minutes how Oscar Pro and Oscar BCI, you remember the BCI related Oscar, compare in terms of their classification performance. So here we did not use any artificially contaminated data sets because we don't need the ground truth anymore so radically. We can only look at BCI performance that have been conducted with real artifacts, and luckily we have lots of them. And then we just compare the performance of Oscar Pro and Oscar BCI. So what we had here in terms of data sets was auditory evoked potentials, yes, and visual P300, so a Speller experiment with 15 and 10 subjects. The auditory evoked potentials was recorded with g.HIsys and 16 electrodes, so kind of a device like this. And the visual P300, the Speller experiment, was recorded with the unicorn, with dry and with wet electrodes. So again, we used the same classification scheme. We had 20 training trials randomized, 2, 4, and 6 test trial averages, also randomized, and 200 repetitions. So on the auditory evoked potentials experiment, this is the evolution of performance, so to speak. So we have the accuracy on the y-axis from 0 to 100%, and we have the individual subject accuracies as the thin lines, and the thick lines are the subject average. So originally, we have about 47% performance without doing anything. When we are applying Oscar Pro offline, we can increase this to 60%. And when we are applying Oscar BCI in real time, we are improving to 65%. So only looking at the change here on the right side, we start at 0. Then applying Oscar Pro, we improve by 13 percent points, and then we further increase that to 18%, all in real time. Now looking at the Speller, same structure of presentation. We have the initial performance at 66%. It increases to 71 when we're using Oscar Pro, and it further increases to 77% when we're using Oscar BCI. So that's a plus of 11%. I can also show you at least one video, which is where Oscar BCI is used. It's the brain body game developed by Martin. And here, probably you can hear the sound. It's a jump and run game where you have to focus on flashing items. And when you focus on the right items, then something changes in the scene. So for example, here, the bridges are created and so on and so forth. So you can see it takes about 3 to 4 flashes until the BCI recognizes that you are focusing on this item. So that's very brief and short demo. I think Martin will talk about this a little bit more throughout the spring school. So this one we will skip. Let me finish my presentation with a review of our initial checklist and providing some conclusions. So if you remember, we had quite some items set up. So first of all, we wanted to have something that eliminates all artifacts, or at least a wide range. So we can fairly say that OSCAR Live, up to some extent, but more than sufficiently, OSCAR Pro is eliminating all the artifacts we see in the data. The question whether we preserve or recover brain activity has been also discussed, and we have shown that OSCAR Pro is recovering brain activity in a very wide to a very wide extent, and also OSCAR Live is doing that based on the compromise we're having there. In the last part of the talk, I have covered the BCI performance, how OSCAR Pro and OSCAR BCI are recovering BCI performance. So that's something we definitely can see up to 10 to 20% roughly we gain in performance when we are applying the OSCAR BCI in real time. We have seen it in the real-time demo that OSCAR provides feedback, so we know when the signal is bad and when it is corrected, and when we probably have to do something about it. And of course, also OSCAR Pro provides that feedback when you're processing the data. We've also seen that OSCAR Live and OSCAR Pro, they produce very realistic EEG at all times. So even though the input is vastly contaminated, we still get very stable results. So that means that you don't have to bother anymore about the stability of maybe classifiers afterwards, about trial rejection. So we can just feed everything into the upstream or downstream pipeline because the EEG is so stable. We have seen that it works out of the box. So I've never ever like configured OSCAR whatsoever. So it just gains all the data and all the parameters it needs directly from the data. Of course, it is necessary to start the recording in a nice setting, a nice way, to provide at least a few seconds of good EEG recording, to make sure that all the internal parameters are set up nicely. And finally, the demand that OSCAR is operating in real time with minimum delay is kind of covered by OSCAR Live and by OSCAR BCI. So there is not one OSCAR that fits all desires, but we have 3 very nice members of the OSCAR family, which in their own way fit their purpose quite nicely. So this leads me to the end of my presentation. Let me thank you a lot for your attention. I see that still many people are online, and I have seen some raised hands, so I'm pretty sure that we have a few questions to discuss.
Thank you very much.
Cheers.
Cheers. Manuel is asking about the pathological brain activity. This is interesting after seeing your EEG, but he means the artifacts in the data. Or if there's pathological brain activity like epileptic spikes inside the data, how does OSCAR deal with that?
Yeah, so whenever the activity in the recorded data changes in terms of the spectrum or the amplitude above a certain threshold, statistically determined, then OSCAR will clean that. So that's what I said on one of the first slides, that pathological activity like spikes or something, they really stand out also visually from the EEG. So those activities, patterns, they will be definitely removed.
Then Bernhard is asking about, do you have some numbers on how it improves the performance of online classification? was in the presentation, but maybe you can summarize it.
Yes, so we have done this for auditory evoked potentials where we gain about 20% on 15 subjects, and we have P300 speller experiment where we gained 11% performance on 10 subjects.
Should artifact removal with OSCAR or without OSCAR done before additional pre-processing steps like low-pass filtering?
So it works best when you already get some low pass, some band pass filtered data. Otherwise, it's doing it on its own. So the best way would be to have standard EEG data ranging from 0.25, maybe 0.5 to 30 hertz. For the OSCAR Live. For the OSCAR BCI, you operate directly in the spatiotemporal whitening domain. This is where you have the standard ERP extraction pipeline beforehand.
What happens to epileptic spikes or beta spindles?
They will be removed. If they stand out from the EEG characteristics, they will be removed. So the rule of thumb is everything that can be recognized by the bare eye will be detected.
But of course, you can open an extra stream when you want to have the spikes. So if you want to have some spindle counting or HFO counting, then send it into an extra stream and send all the other data into OSCAR for a clean EEG stream. Bernhard is asking, how does it compare to other methods like ESNR, threshold rejection, auto rejection, and so on?
So I've shown this last year where OSCAR performed on par or outperformed ASR. So ASR is basically the only competitor we have when it comes to online EEG artifact removal, because all other methods we researched or we found are using reference signals or done offline or something like that. So ASR, the adaptive artifact subspace reconstruction, this method was our reference method, and we showed already last year that we are basically outperforming it and we are removing artifacts better. And this year, so in the last year, lots of things have happened. So OSCAR got much, much better. So it definitely outperforms ASR.
Fatima is asking, do you use some machine learning or deep learning to remove the artifacts?
No.
Easy answer. Is it possible to choose a specific artifact to be left out?
Not really.
But like mentioned before, you can always open an infinite number of data streams. In one data stream, you can, for example, apply OSCAR and you get clean EEG data. On another data stream, you can count HFOs, and on another data stream, you can do something else. So it's completely flexible in g.HIsys Professional, and you can do many, many channels. So she is saying, for example, if we need eye blinks in the EEG, what would you do?
If you need them?
Yeah.
Well, mainly those eye blinks occur in the frontal channels. So you could, as Christoph mentioned, or inspired by Christoph's answer, you could run a parallel stream on the frontal channels, and you can keep that and don't pass it through the OSCAR pipeline. What you can also do, if you really want to have only the eye blinks, you can then subtract the original signal, or the OSCAR signal, sorry, the OSCAR signal from the original signal. So this actually removes all the EEG, but only the eye blinks remain. So that will be actually a nice eye blink extractor.
Alem is saying that he's using the g.Sahara system at the University of Science and Technology, Oran. And he would be interested in seeing some examples how it performs to engage with g.Sahara. I guess you're using g.Sahara hybrid at the moment?
Yes.
Is it dry or wet?
Right now it's wet. We tested it with dry, but as I said, I wanted to be on the safe side for this demo. But essentially, the only thing is that with dry electrodes, the amplitudes are a bit higher and it fluctuates a bit more. but the overall processing scheme is very much the same. So there is no objection to that. We can try that.
And he's saying, thank you for g.tec for the spring school. Pleasure. Thank you for being here. Bernhard wants to know if it's open source. Maybe I can answer it. So the algorithm is embedded in the headsets and amplifiers because they're running with a very high sampling frequency. And this is what we need to make them really efficient. So it doesn't make sense to put it out of the device because the efficiency is just better with higher frequency. Stanislav says, great presentation. I'm wondering, does reducing the number of electrodes or resampling affect Oscar's runtime?
Interestingly, not so much. So we found out that the sweet spot of channels is about 16. It also works very nicely with 8 channels. That's you have seen that the results with 8 channels are also pretty astounding. You have to consider that when you're maybe subsampling or upsampling, especially if you're kind of interpolating or something like that, you could get collinearity in the data. So that could mess up Oscar in the whitening process. I wouldn't try to do that. But with regards of computational demands, we have seen that we can go up to 64 channels, and it runs in real time perfectly well. So that's not an issue.
Then is Oscar Pro denoising EEG in the frequency domain?
No, not really. It's transforming the data. Of course, it's a multi-band approach, so we are addressing various frequency bands. But the domain, the processing itself is buffered time domain processing.
And Raji wants to know if Oscar works with other devices than g.tec devices. This is not the case because it's embedded in our devices. And with that, we have answered all the questions. Thank you very much, Johannes, for the nice demo.
Thank you.